So in this presentation, we're going to have a look at quantum computers and especially focused on post-quantum cryptography. So I'll give you an outline of how quantum computers work basically and how they can crack our public key encryption methods, but we'll mainly be looking at the standards that are being set up for post-quantum cryptography. So we've had Moore's law for many years, and when you think about it, the processors and transistors started to be integrated around the start of the 1970s, and then basically we followed Moore's law after this, where roughly the number of transistors on a microchip doubles every 2 years. So here we are up here with our modern processor with 50 billion transistors actually on the device. But unfortunately, we've hit the limit as to the size of the transistors that we can have. We're looking at even less than 5 nanometers for the size of the transistors, and there are only certain places in the world which can actually make these small transistors, such as the TSMC factory. So how do we now expand on to that and keep increasing the power of our devices? One way is to go into the optical domain. So rather than using silicon and binary digits, we use things are called qubits. And these, we convert our bits into a qubit, and where we can actually measure the state of a qubit. So the qubit itself could have various forms of spin and rotation. So for this, we replace our existing normal Boolean gates with these ones here. This one will rotate 180 degrees on the x-axis for the qubits. This one 180 on the y-axis. This one on the z-axis, and so on. And we can create these qubit gates that allow us to be able to build up our circuits as we would. And the other thing that we have is what's called superposition. And with superposition, we can actually have a qubit in different states. And it's only when we actually measure the state do we actually determine in which state it is in. And it was Peter Shor who came up with an algorithm that allowed us to be able to break all of our existing public key encryption methods. So that's RSA, the factorization of N and of P and Q for the modulus, and also elliptic curve cryptography. So with this method that he created, he found an algorithm that allowed us to be able to find out the 2' numbers which were used in RSA and also solve the discrete logarithm problem which is used in elliptic curve cryptography. And then we have Grover's algorithm. Grover's algorithm defines that it's possible to build up a massive table of keys and then try each of these keys at the same time. With this, we can aim to break symmetric key encryption and also hashing methods up to 128 bits. So the main thing from Grover's algorithm and Shor's algorithm is that we need to deprecate and then remove our existing public key encryption methods, and we need to upgrade our symmetric key and hashing methods to 256 bits. And it's happened recently in the US that there was a memo signed that will define that all national critical infrastructure systems will migrate to post-quantum cryptography within a reasonable time limit. So this is a number of agencies which are coming together to be able to set this up, including the Cybersecurity and Infrastructure Security Agency, the NSA, and NIST are all going to work together to be able to migrate away from our existing public key methods towards post-quantum cryptography. and which will be robust against quantum computers. So this is the basic timeline. The NIST project for post-quantum cryptography started in 2006, and then around 2004 onwards, then the standards were ready for both, as we'll find, key exchange and also for digital signatures. By 2031, there's a 1 in 7 chance of breaking RSA 2K, and then we can see here, then there 1 in 7 by 2026, and then 1 in 2 by 2030 that RSA 2K will be broken. And the problems that it solves is that these methods, such as factorizing and the discrete logarithm problem, are cracked by quantum computers. So we need to migrate away from these problems, which are hard at the current time, but will not be hard when we implement quantum computers at scale. And basically the method is that we have two prime numbers which relate to the frequency of a wave. Then we can actually measure the point at which they cross over, and that should relate to the modulus, and from that we can find the P and the Q for each of the waves, and thus factorize modulus and RSA. So let's do a quick Crypto 101 so that we understand where we are. Okay, we typically talk about Bob and Alice as the people who communicate, and then Eve is the evil adversary, passive adversary. Symmetric key, we use the same key to encrypt as to decrypt. Then with a one-way hash, we take a fingerprint of the data and we can have the hash there. MD5 shouldn't be used anymore, it's insecure. SHA-1 is a 160-bit hash. It's becoming insecure, and we should always move towards 256-bit hashes, such as with SHA-2, SHA-256, and SHA-512. We can also use SHA-3 and Blake2 if we need. If we want a variable length hash, we can use these XOFs, such as Shake and Blake2XB. For key exchange, that also uses public key encryption methods, where we generate a secret, we take G to the power of A mod P, G to the power of B mod P, and then exchange them over, and we end up with the same shared key in the end. Then we have public key encryption, and we can also use this for key exchange. For this, we create a key pair, a public key and a private key. We encrypt with the public key, and then Alice will decrypt with the private key. So we can use public key encryption to be able to encrypt our data. Where public key encryption typically comes in is with signatures. With this, we take a hash of a message and we sign it with our private key. We then use the public key to be able to verify the hash there. Okay, so this shows roughly what's happening when we connect to the internet. Basically, we use elliptic curve Diffie-Hellman to be able to exchange a symmetric key, or to be able to generate a symmetric key, which is used for the encryption. To be able to prove that it is Alice that Bob is connecting to, then Alice will sign a message with her private key. Bob will verify that with her public key. She gets the public key from Trent, who creates a certificate, X509, and signs it with his private key, and then Bob can take Alice's public key from them. This is the way that the internet security typically works. Okay, so let's look at the post-quantum standards that have been developed. Basically, there are 5 main problems that are still hard problems when it comes to our quantum computers. Hash-based methods have been around for a while and basically involve Merkle trees where we can actually hash and then keep hashing and have a root. It's a very, very secure method and well-defined. We can have code-based, which is a bit like our error correcting codes that we would get on a CD-ROM. Multivariate is multivariate cryptography. I won't go into the details here, but the one that's used mainly for modern systems is lattice-based methods. And then we can have isogenies, which have the advantage of being able to use the Diffie-Hellman method from the past. But it is lattice methods that provide the best compromise of performance and key size. Okay, in the first competition, what happened was we had a shortlist for the key exchange and public key encryption methods, and the one that won was Crystal's Kyber. And then for digital signatures, we had 3 that were the winners: dilithium, Falcon, and Sphinx Plus. All of these are hash-based apart from, are lattice-based apart from the hash-based one here for Sphinx Plus. Okay, to give you an idea, the key sizes for Kyber for the key exchange, 800 bytes for the public key, about 1600 bytes for the private key, and then the ciphertext that's passed is 768. There's 3 different levels, typically defined 1, 3, and 5. This is equivalent to 256-bit security. This one is 128-bit. So if we want more security, we use the larger one, such as Kyber 1024. When it comes to signatures, then the public key is bigger than we have just now. This is the current keys that we have for elliptic curve and for RSA. So we're going to increase these 1300 bytes or so for the public key, 2500 bytes and more for the private key, and about 2400 bytes for the signature method for dilithium. Okay, so for key exchange, what we can do is we can have a hybrid method where we can put both the Kyber and ECC. So this is now called MLKEM, if you're interested, or FIPS 203 from there. So we can exchange both elliptic curve and Kyber, and that will give us 864 bytes, which is quite good because it's less than the size of a TLS packet. When it comes to digital signatures, then we have with dilithium for the key, public key, it's about 2500 bytes, which would mean that we'd need 2 data packets to send the public key. Sphinx Plus is much larger, and we'd need 12 packets to be able to send the key, public key for that one. So the migration overall, this is what we would see. We see the hashing methods must move to SHA-256 and SHA-3. Our AES methods for our symmetric key must move to 256 bits. So this is defined by 2030. Then our key exchange methods, we use elliptic curve Diffie-Hellman. We use X25519, that uses curve 25519, and we can also use public key exchange with RSA. This will move towards MLKEM or FIPS 203, or we can use a hybrid method of using this existing method along with the MLKEM key exchange method. HQC has just been approved as a code-based post-quantum cryptography standard. So this will give us an alternative to MLKEM. We can use HQC. When it comes to public key encryption, we can use RSA OAEP. And for this, we can still use our MLKEM or this HQC for that encryption. When it comes to signatures, the signatures we use are ECDSA, EDDSA, RSA PPS, and RSA PQC S1 1.5. Those are the typical signatures that we would use on the internet. And these will move towards dilithium, which is MLDSA, SLDSS, which is Sphinx Plus, that's a hash-based method, Falcon, which is a lattice-based method, it has the advantage of having smaller keys than dilithium, but the performance isn't as good. And then there are other methods which are going forward towards standardization too. Okay, so the FIP standard 203 is for MLKEM, so that's for this one and this one, and 204 and 205 are for the two signature methods that we have here, along with Falcon being created. So then by 2035, all our existing public key methods and key exchange methods must be gone, and then they will be replaced by either improved symmetric key and hashing methods or our post-quantum cryptography. Okay, so that's been a quick overview of post-quantum cryptography. Thank you.